So today we're happy to welcome Kilian Risse from EPFL, who will tell us about supercritical tradeoffs for monotone circuits. Please take it away, Kilian.
Yeah, thanks for the introduction. This is joint work with Mika, Gilbert, and Dmitry. And if you have any questions during the presentation, please just ask. I think we have more than enough time to also answer the stupid questions. So we'll see. All right. So instead of telling you what this will be about, I'll just start with the main technical contribution of ours. It's such a nice object that I can just talk about it in isolation. Okay, so before introducing this game, which is somehow the heart of our argument, I need to tell you something about some strings. So we want to consider strings of some even length n, which are over the alphabet of a red opening bracket or a red closing bracket, a blue opening bracket or a blue closing bracket. And we want that these strings are well parenthesized. So what I mean by this is that if you have some opening bracket, then you always have a buddy, like a partner, which will be the same color and it's closing. Okay, and the colors need to match. So for example, this string here, right? I matched each of these bracket pairs together, and we really want to think of these as one. So going forward, whenever we actually have one opening red bracket, we always think of also having the buddy that is paired up with this opening bracket. Okay. And then finally, we want that the initial symbol of the string is a red opening bracket, and we want that the final position of the string is a blue closing bracket. Okay. Now it's not so hard to see that actually there is an index so that a red closing bracket is followed by a blue opening bracket. Okay. And how can we convince ourselves? Well, we just start with, say, the red opening bracket here. We know by this property that it has to be a red opening bracket. Then we jump to its buddy, the red closing bracket, and we look at the next position. Now, either this position is a blue opening bracket, in which case we're done, or we have another red opening bracket. If it's anything else, then we are not well parenthesized. Okay? So then we can go to this red opening bracket. We can go again, jump to its buddy, find a red closing bracket, go one position further and see what's here. In this case, again, it's a red opening bracket. We go to the buddy, the red closing bracket, and now we look at the next position. And here we actually have found this index I, which is a red closing bracket followed by a blue opening bracket. Okay, simple thing. All right. Now we want to turn this simple claim into a game, and we do it as follows. Namely, we will have a prosecution and a defendant. And now the defendant claims that there is no such index I, where the I symbol is a red closing bracket and the I plus first symbol is a blue opening bracket. So the defendant is the liar and we are the honest prosecution, and we want to catch the defendant lying. Okay. So how do we do this? So the prosecution may query in every round. So it's a game that proceeds in rounds. So the prosecution may query in every round some index I. Okay, and then the defendant needs to respond. So the defendant needs to respond with a bracket pair. All right, so maybe the prosecution wants to know what's here at this index here, and then the defendant may answer with some bracket pair. Maybe here it's a blue opening bracket and the corresponding closing bracket is over here. Okay, so we can query a position, and in return we will get a bracket pair. All right.
So we'll get the bracket in position I And the body of this bracket, is that what defendant
Exactly.
should supposedly?
It has to answer like this, like reinforced.
Okay.
And if
so
it answers in any other way, the prosecution just immediately wins. Okay.
Okay. But I mean, it will be like a blue bracket. In this case, it will, since I see a blue opening bracket, I know I will now find a blue closing bracket to the right. And if the other position is something else, then obviously the defendant already lost. That's what you're saying. So without loss of generality, since I see a blue opening bracket, I will see the second answer will be a blue closing bracket to the right, and I will learn the position of that guy also.
Yes.
Obviously. Okay, good.
Precisely. And so then the prosecution wins whenever they find an index I, so that the red closing bracket is actually followed by the blue opening bracket. This is really like catching the defendant line, or if it's ill-parenthesized. So this is what Jakob was referring to. So for example, if you have a blue opening bracket matched with a red opening or closing bracket, if these just don't match together. Or if you have, like, say, a blue bracket, if you have a blue bracket like this, and then some other bracket that like overlaps, like that the bodies are like overlapping, right? This is also an ill-parenthesization. Okay. All right. So now it's not so hard to see that the prosecution can always win this game in n rounds by just querying everything, right? Once you queried everything, either it's somehow ill-parenthesized, it's a string that we don't care about, or otherwise there is actually such a red closing bracket followed by a blue opening bracket, right? So it's not hard to see that the prosecution can always win the game in n rounds, okay, by just querying everything. Or if you want to be a bit smarter, you can just do the proof that I showed you on the previous slide, where you just always jump on with the red brackets until you find the blue opening bracket or some misparenthesization. Okay, but like in either way, in the worst case, it will take you n rounds, or well, maybe n over 2 rounds, because we always get 2 indices, but never mind. All right, so to actually make this a bit more interesting, we will want to somehow limit the prosecution. Okay, and so now I want to look at the prosecution, which may only remember W many bracket pairs at once. So I constrain the prosecution, and now the question is, well, do we still have such a winning strategy for the prosecution that wins against any defendant? Okay, and now, because we're limited in memory, in each round, the prosecution can either query an index as before, or otherwise it can forget a bracket pair, so that it can make space again, so that it can query new things. So forget a bracket pair. Okay. Game is clear so far? All right. Well, that was a bit quick, yeah. But if you have questions, please ask. So now the obvious question is now, well, what is the minimum memory that the prosecution needs to have so that we can still win against any defendant, right? And now I want to open the floor to everyone who is attending. And what do you think? Like, do you have any suggestions of what the prosecution could do? What would be a good strategy?
2 brackets should be enough, no?
2 brackets. Okay, why?
Just do what you did.
Okay, let's see what happens. So we query this first position here, and we get its body over here. Okay, and I'll like try to indicate that these are bodies, these bracket pairs.
Or if this fails, I want to understand why, which would be instructive.
Yes, I forgot to say something, so I'm very thankful that you suggested it. So then we look at the next position, and we have again a red opening bracket because I mean, yeah. Okay.
And now what I wanted to do is just to say, screw it. Now we have a much smaller game, so I can forget everything to the left, and that is probably
Yes.
false. And
Yes.
you will explain to me why.
So we'll forget this, and now the defendant is asked, well, what's happening at this position here, right? And now the defendant may just answer with, oh, actually, I have really like a blue bracket pair that just wraps this red guy. And what do we do now? It's very
Clearly, the
unclear.
defendant is lying. This is outrageous. I mean, he shouldn't do
Exactly.
this.
So the defendant may be lying and it may change its answers as we move along, which I actually forgot to mention before. So it doesn't have to answer to a base truth, but it can just answer however it wants to. Okay. And this is, yeah, thanks for asking this question. And this shows that this gives quite some power to the defendant. Okay.
What about you try binary search? Well, each time when the defendant branches into, say, the left, you remember the right largest bracket he has provided you.
Okay, we're getting closer. So what Shuo is asking, I hope, or suggesting, not asking, is like we query down the middle, right? We ask in the middle, so what's happening here? So now the defendant has to answer somehow. So maybe it gives us a bracket pair, so something like this, right? And now we probably are interested in what's happening here on the left side, right? Because on the right side, if we ask the defendant something on the right, the defendant may just answer with blue bracket pairs, and it's actually consistent there, right? There doesn't have to be a solution on the right-hand side. Like everything may be blue, so we don't have any red closing bracket pair, like bracket followed by a blue opening bracket. So it's kind of pointless to query anything on the right-hand side here. So instead, we want to focus on the left side. And now, I mean, it seems natural to just recurse, right? So we will now just recurse on here, right? So we want to recurse. And so what do we do? Well, we again query down the middle, right? So we may query something like maybe this position here, this one here. And then as an answer, we may get something like 2 red bracket pairs. And we continue going until this piece is very small, right? And we continue to recurse on this, I'll call it separation interval, where there's on the left side we have a red bracket pair, and on the right side we have a blue bracket pair. So it's somehow the separation interval between these two colors, and until this interval becomes very small. And at that point, the defendant has to answer with something a bit smarter, right? It cannot just answer again with something within this interval. Because if it does, we actually catch them lying. So what they can answer, or what we hope that they will answer with, is some kind of bracket pair. So right. So let's think of this now as very small here. So now they have to answer with something that actually leaves this interval. So maybe, right, we create the middle one, and then we get a bracket pair like this. Okay. So now we return from the recursion, and now we can actually forget these, and now we actually have made some progress here on the left side, on the large one. Why did we make some progress? Well, we now cover more positions with a bracket pair. So what do I mean by this? I mean that if you look at all positions that are covered by a bracket pair in this interval, in this case, it's like all these that are contained within this red bracket pair, this has grown compared to before, right? Before we had nothing here. maybe like we had these two covered, right? So now we can continue playing like this, right? And every time somehow the recursion returns, we'll have a bit more area covered. And ultimately, when we continue playing this, ultimately we'll get a bracket pair which is very big here, right? Maybe something like this. And now in the next round, when we ask the defendant again for a bracket pair, we will query here, right? Because this is not a separation interval, and we'll get something which goes beyond the middle, right? And now we can forget everything that we learned here on the left side, except this last bracket pair that we received. And now we can continue our recursion here on the right-hand side. Okay. So what is the idea? The idea is you split down the middle, and then you invoke a recursion. You have the recursive guarantee that either this recursion will find you a solution, or it will find a bracket pair which will cover one of the endpoints of the interval. Okay. So I have this formalized like in some pseudocode here. So what does the prosecution do? Well, we first we query the index in the middle, down the middle, right? So we query the index here. And then we receive the indices of our answer. And then while these indices are within our interval that we're currently looking at, and we have no solution, so this meaning everything is well parenthesized and so on, and we don't have any like red closing bracket followed by a blue opening bracket, we find the separation interval, right? So let me draw an example. So right, we query it down the middle, then we find our separation interval. This is now this interval here. And now we invoke the prosecution recursively on this subinterval. Okay. And then once this prosecution returns, it will return with a bracket pair which will actually leave this interval, right? Or we have a solution. Okay. So in this example, it may, for example, answer with a bracket pair that leaves now the interval down here. Once we have achieved this is good for us because now we have made progress, we cover a bit more positions, and then we continue recursing on the separation interval over here. Do you have any questions about the prosecution strategy?
You mentioned how to forget things.
Yes, very, very good. So we always forget. So we always forget. So we always forget bracket pairs contained in some other bracket pairs. And we also forget any brackets that are not within the separation interval anymore, or right adjacent to the separation interval. Okay. So in particular, if you have done some work over here, and maybe you have some bracket still lying around over here, like maybe you have this one lying over here. Once you jump recursively now to this part here, then you can actually forget about these.
This you do just to save memory.
Yes.
So could you explain, suppose you have this picture where we started with the blue guys, and now suppose I get a badly parenthesized, so the red guys are enclosing, say, the rightmost blue
Okay, so
bracket, then what will the prosecutor do?
So you mean like you have this bracket pair?
Or maybe that doesn't happen?
Well, no, but the defendant may very well answer with something like this.
Yeah, now what do you do?
But then you're done, right? Because this is an ill parentization, so this corresponds to a solution.
Regardless of how far away these are?
Regardless of how far away these are.
Ah.
Like once you have overlapping bracket pairs, you're done.
Okay. This wasn't clear to me. Thank you.
Sorry. Yeah. So okay. Maybe like to be very clear. So no solution here. What I mean by this is either we have found a red closing bracket followed by a blue opening bracket, or we have some misparenthization.
This means
some
because the
misparenthization
misparenthization wouldn't be obvious just from staring at the string, right? But you actually don't just have the string of parentheses, you have this meta information about the pairing.
Yes, exactly. We always think of the pairs, they always come in tuples.
Okay.
They're always fixed. You're also not allowed to reshuffle them later, the defendant. So they really have to answer with a bracket pair. And you get this pair, and then you can really think with these gray arches above.
Okay, good. So with this enhanced understanding, an answer like this means that as soon as I see this, then the prosecutor has won. So this means what? This means that the defendant will always play inside an interval that you're interested in. So here, basically, the defendant could play either to the left of the blue guys or the right of the blue guys if the defendant plays red.
Yes.
Or it could enclose.
Yes, exactly. So now we play on here, right? Let me make it a bit bigger. So maybe we actually play on this large thing here, right? So now the defendant, if the defendant is smart and like there the prosecution queries down the middle, whereas like this point here, then the defendant will either answer with a red bracket pair that lies really close together or a blue bracket pair that is right next to each other. And like the defendant now wants to minimize the number of indices that it actually covers. Okay.
And then when the defendant answers like this, we just the interval will be the red blue. We'll just go to the interval that is delimited by red and blue parentheses on either side in this case.
Yes, exactly. So this is the separation interval.
And the same thing, if for some mysterious reason the defendant answered with a larger red parenthesis pair, then you'll just go to exactly the same place.
Yes.
Okay. And if one of the red parentheses would actually be outside of the shaded area, then we have already won. Just recapping what you said before. Good. Thank you.
Wonderful. Okay. So I hope it's clear that this strategy requires roughly order of log n memory, like order of log n many bracket pairs. So for each bracket pair, I consider it as one. Okay. So it requires log n many bracket pairs to remember. And now, so the memory we successfully minimized. So we brought it down to log n. And now the question is, what happened with the rounds? Does anyone see how many rounds this strategy requires? Right? If we are on the top level of our recursion, then we have like n indices. And now we query down the middle. The defendant may answer with a bracket pair that lies right next to each other. And then we have to recurse over here. Now, what can happen? Well, the defendant may just answer with a bracket pair that is right, like enclosing the red one very tightly. Okay. So this means we have done one recursive call, and all we have gained is like we cover two more positions, right? Because now we forget everything on the right side and this one in the middle. And now we continue recursing on the left-hand side. So right? We cover 2 more positions by doing one huge recursive call. And so now we go to the other side and we do again this huge recursive call, and then we cover 2 more positions. Okay. So this means that the top level recursion will have to do like linearly many recursive calls down, right? And if you think about a bit about it, you'll see that the number
So what
of
I didn't
rounds,
see, it seemed like you'd get a logarithmic number of rounds, but that's very wrong, right? And the reason that's very wrong is because you're saying now, oh, you're saying like what will they will have some kind of recursive call, and when we return from that, what will the defendant do? It will try to play red around the enclosing blues and
yes,
force you over to the other side. So
exactly.
it's not binary search because I'm able to force you to explore both sides somehow.
Yes, precisely.
Okay.
So I jump back and forth between these 2 sides, and each time I just gain like 2 positions. So I have to do linear number of like recursive calls to actually finish this strategy in the worst case. Okay. Now, if you think a bit about this,
But that is also, and here you're using that once I move over to the other side, you were so stingy with your space usage that you don't remember all the stuff you had that before. If you would have just remembered a little bit more, then you would have caught me quickly, but you forgot everything.
Oh, of course, much, much faster. We'd be incredibly fast. Maybe. Right. But yes. So yes, but we forget everything. So we have to start anew on the left side, and we have to start anew again on the right side. But the point is that this requires a huge number of rounds. It requires roughly like n to the log n. There's some epsilon here in the exponent. Many rounds for this strategy to actually succeed or finish. Okay, because like on the top level iteration, we do n hops back and forth. On the one down, we do like n over 2 and so on. And yeah, this gives you like this n to the log. All right. In case you got lost, so what have we shown so far? That we have this prosecution defendant game. The naive strategy is just to query everything, right? This requires n rounds and n memory. And now we have seen this recursive approach where we actually only require order of log n memory, but then the number of rounds is n to the epsilon times log n. Okay, so as we reduce the memory usage, the number of rounds exploded. And now the question is basically what Jakob was hinting at was like, okay, fine, but in our strategy, we were very, we forgot everything on the recursive call. What happens if we actually remember some things? Can we do better? Can we reduce the number of rounds as we reduce our memory usage, right? And this is actually our main result. Our main result says that this is not possible. So what we show is that if you have a strategy which requires W much memory, then you need this huge number of rounds. You need these almost n to the log n number of rounds. Okay. Are there any questions at this point? Okay, so as we reduce the memory, the rounds blow up, and this is really necessary. So this is what is called a trade-off result, right? So what is a trade-off result? So right, we have, if I draw here the memory, right, we can do n memory and we can do n rounds. This is like this 0.1 here. This is our 0.1. And we can reduce the memory. We can reduce the memory to roughly logarithmic, right? But then the number of rounds blows up. So we get this data point here, this 2 here. And now what we're saying is that, well, anything down here is not really possible, right? So this red area here, there is no strategy of the prosecution that requires little memory and few rounds. Okay. And actually, it's even more interesting because if you just want to reduce, like minimize the number of rounds, you can always achieve an upper bound of n, right? Just by querying everything in any prosecutor-defendant game where you have n things to query, like n objects that you can query. And this is what's called a supercritical trade-off, where you don't just have a trade-off result, but you actually have a trade-off result so that when you reduce one measure, the other measure grows beyond its worst case performance if you would just optimize the number of rounds. Okay? So this is called a supercritical trade-off. Okay. All right. Any questions? So you should have one question. And this is, well, my title was about monotone circuits, and so far I really have not talked about monotone circuits. And I'm telling you, this is our main result. Right? So where are these circuits?
One other question, if you flip back, sorry, it's like how tight is this? Like the way you drew it, it's like, you know, the red exactly matches the points, so it's beautiful. Is it that tight, or is there any slack in the upper and lower bounds?
There's a little bit of slack here,
but not too much, or what?
Well, here,
like what you can do, the upper bound?
So the lower bound is n to the omega log over log log. And if I remember correctly, the upper bound is n to the log over log, log w minus log log, or log w over log n. So this is the upper bound, and this is the lower bound. So we're off by a little bit. Yeah. Does this answer your question? Sorry.
Yes,
log
but it doesn't.
W. This is correct.
I don't immediately get a good sense of how much this is. But okay, I'll just have to meditate over this.
Yeah, so if you look at W equals log n, then you get n to the log n over log log as a lower bound, and the upper bound is n to the log n. So this is like the...
Okay, thanks.
The slack that you can play at the extreme when you actually require log n memory.
Thanks.
All right. So I told you I'd talk about monotone circuits. And so so we can actually, from this result, we can quite directly get monotone circuit supercritical trade-off. So let me tell you how this actually works. So I summarized here in like just the theorem that I claimed before. So I claimed that there's a prosecutor defendant game, so the prosecution has a winning strategy using log n memory. While any winning strategy in W memory requires actually n to the log n over log W rounds. Now, if you're somewhat familiar with resolution and proof complexity, you will actually see that I just kind of hid resolution here from you. And really what this theorem is saying, it's saying that there exists some formula F. I'll get back to this just a second. Let me first explain the theorem. so that there is a with log n resolution refutation. So in particular, the memory usage translates to width of resolution. If you don't know resolution, just ignore this discussion. It's not important for the rest of the talk. And any width W resolution refutation is actually of depth log n to the log n over log W. So the rounds translates to depth in resolution. Okay. So now, what I told you before in this prosecution defendant game language, you can translate this directly to resolution language, and you now get a supercritical trade-off, trading off width versus depth. Okay. And one thing that you need to be a bit careful about is that you actually, in this translation from here to here, you need to be careful about this formula F and what kind of a formula you actually see. So the formula is just encoding the claim of the defendant, namely that there exists no red closing bracket followed by a blue opening bracket, okay, while the string is well parenthesized. And now you need to make sure that this is actually a 3CNF for reasons that I'll explain in a bit. So you need to like somehow introduce extension variables and so on to actually be able to encode this claim. But just trust me, like you can do pretty much whatever at this point and it will work out. So we chose to just introduce all possible extension variables on one index, and then you can show that everything works fine. Okay. So this F encodes the claim of the defendant. All right. Questions? So, okay. So this is somehow explaining that what I told you before is really a supercritical trade-off resolution. Now, the cool thing about proof complexity is that we have like lots of tools that connects proof complexity to other areas, such as monotone circuits. And there is actually the standard, or by now standard tool called DAG-like lifting, which lets us take results in proof complexity and somehow lift them to monotone circuits, okay? And if we just combine our theorem here with this DAG-like lifting technology, we obtain the following supercritical trade-off for monotone circuits. Namely, we can show that there exists a monotone function f such that it has small circuits. It has like circuits of quasi-polynomial size, monotone circuits of quasi-polynomial size. While any such circuit, any small circuit, any small circuit needs to be of large depth, okay? So all monotone circuits, they compute f in polynomial depth, in like any polynomial depth, require exponential size, okay? So this is saying that if you want to minimize the size of your monotone circuit, then this circuit will be super deep. It will be like of depth quasi-polynomial, basically. Okay? And because we know that the depth of a monotone circuit in the worst case is linear in n, this is again a supercritical trade-off, like one of these size-depth trade-offs for monotone circuits. All right, so do you have any questions or, yeah?
And a possibly evil question is, given that I understand the 3CNF formula that you're talking about, is it the 3CNF formula capital F? Is it easy to say something about what this monotone function lowercase f is? Like, what does it look like? How hard is it to compute? These kind of things? Or it's just, this is painful.
I never worked it out, and I don't know. I mean, right, you compose f with indexing, and then from that you extract a function, which is a bit annoying. I'd have to work it out. I never tried to work out what this function is.
Okay, so not immediate to explain.
No. Okay, so this is really the main result of our paper. Unless there are questions, I'll tell you a bit about the history of these supercritical trade-offs, and then I'll move on to the proof. Even though I already took like 45 minutes, so maybe just history and then the proof is in the second part. Okay. So let's look at supercritical trade-offs. So this is something that was first observed by Beambeck and Impagliazzo for resolution size versus space, and for Berkholz with resolution depth versus width. But like the real, like somehow person that popularized these supercritical trade-offs and like really asked the question of whether we can prove more such trade-offs was Rasparov, who proved these tree-like resolution depth or size versus width trade-offs. And I think the contribution or the main contribution of his paper is actually introducing this idea of hardness condensation to prove complexity, and somehow explaining how you can use hardness condensation to prove supercritical trade-offs. And on a very high level, how this idea goes is basically that you start with some formula F, which has a subcritical trade-off. So meaning we have a trade-off between two parameters, but as we decrease one parameter, the other one has to grow quite a bit, but not beyond its worst case behavior. Okay. So you start with such a formula that exhibits such a subcritical trade-off. And now what you want to do is you want to reduce the number of variables. So right here, I drew the clauses on the left and connected the clause with the variables that it contains. And now what I want to do is I somehow want to reduce the number of variables. So here I had n variables. I want to reduce number of variables to some n prime, where n prime is much, much smaller than n, while preserving the hardness. And what Rasparov did was he would replace every variable xi by somehow the XOR of some of these new variables. And then if you have a good enough expander over here, like that describes this incidence, if you have a good enough expander there, then you can actually show that you can retain the hardness. And by retaining the hardness, now you actually get a formula which has supercritical trade-offs in the number of variables, right? Before, like reducing the number of variables, we already had a trade-off. Now we reduce the number of variables, and as the number of variables shrinks, like at some point you will actually get a supercritical trade-off. The downside of this strategy is that as you reduce the number of variables, your formula size will blow up. So the composed formula, which is like this formula F with these XOR substitutions, if you want to write this out as a CNF, it gets really large, and actually you don't get a supercritical trade-off in the size of the formula, but only in the number of variables. Okay? And this was the main bottleneck before our work to actually prove monotone circuit lower bounds. So everyone, or it was well known that we would like to have supercritical trade-off in the size of the formula, because then we could apply this tag-like lifting to actually get a supercritical trade-off for monotone circuits. All right, so just to summarize, Rasparov introduced this idea of hardness condensation to prove complexity, and basically all future work except ours actually built on this idea. And really there was a flurry of work that followed like this paradigm, but the downside is that you only get a supercritical trade-off in the number of variables and not in the size of the formula. But nevertheless, like this work had some really nice applications for lower bounds on the stabilization time of the Weisweiler-Lehmann graph isomorphism algorithm. So this was first done by Berkholz and Nordström, not for graphs, but for some other structures. And then Grohe, Lichtner, Neuen, and the last one, Grohe, Lichtner, Neuen, and Schweitzer, they proved this amazing, basically optimal lower bounds on the stabilization time on the Weisweiler-Lehmann algorithm. But at the heart of it, it's really a supercritical trade-off hiding there. Okay. Any questions so far? All right. Last but not least, I should mention that there is a concurrent work by De Resende, Janet, Fleming, Nordstrom, and Pang, and they also exhibit a supercritical tradeoff for monotone circuits, which goes about as follows. So they exhibit a monotone function f, which has small circuits. So it has a monotone circuit of size polynomial in n. But if we look at any monotone circuit of low depth, then its size blows up. Okay. So again, if you want to have a small monotone circuit computing this function f, it needs to be of fairly large depth if you want to have it of small size. All right. So just to like give you comparisons. So we remember the parameters. So for our theorem, we got here like something of order roughly log n. We constrain the depth to polynomial in n, but then we get a blow up of exponential in n to the some epsilon. Okay. So in that sense, our blow up is much larger than theirs. On the other hand, their blow up occurs much earlier than it happens for us, right? We start out with a formula of quasi-polynomial size, but then we need to actually restrict the depth to polynomial in n, right? Like there's a really like a large restriction in comparison to the size. However, the work by De Resende and the others, they can go from polynomial size and only need to restrict to polynomial depth. Okay. So our blow up is somehow exponential, while theirs is only polynomial, but their trade-off already occurs at a depth which is polynomial in the size of the upper bounding one. And as such, these trade-offs are incomparable. Okay. Let me just mention that their proof goes also through proof complexity, like similar on a high level, the proof follows the same ideas. But while we use this bracket game at the core of our argument, they use hardness condensation, like a much smarter way than Raskorov used the hardness condensation, so that the formula doesn't blow up too much. And finally, it should be mentioned that they actually have an application to I-spiral Lehmann, which we lack. So because their argument is based on Zetin formulas, you get a direct link to graph isomorphism questions, which we lack, or we don't really know how to do. So yeah, I think I'm out of time for the first part.
I mean, it's only 10 to 3, so.
Well, I think it's a good point to stop here. Like I did all the preliminary or the history, what happened, and our statement, and now the next would be the proof.
Yeah, that's another matter. Like you're in charge, basically.
Yeah,
so if you say that now is a good time for a break, then by definition now is a good time for a break.
It's a good time for a break. We'll take a break now, and we can reconvene in 10 minutes. And
except it's a good time for questions before the break from the audience.
Absolutely.
We've had a few questions. I've done my best to provide my usual supply of stupid questions, but maybe we also have some intelligent questions from the other members of the audience. Comments, protests.
I wanted to make sure that one of the lower bounds was independent of the memory required, right? N to the power log n by log n.
And no. So you meant what I scribbled here. This lower bound holds for width equals log n. Does this answer your question?
Yes.
Okay. I mean, in a sense, it shows that you cannot have a strategy in constant memory, because in constant memory, you cannot have this many rounds. You can have at most n to the c many rounds. Sorry, I should show it here. So if we have a constant here, then we would have like a lower bound of n to the log n, but it can only be of size polynomial. So it somehow shows that you need memory growing with n, but we cannot really lower bound it with log n. It's a bit lower. Good question. Thank you. Anyone else?
Sorry, can I ask about the memory log n? Is it so can you with one query get the entire pair and the pointer to the other
Yes.
bracket as well?
Yes, I charge one memory usage per bracket pair.
Okay.
So if you want to do it in bits, it's more like log squared, because each bracket pair actually requires log n memory to write down, just because you need to write down the difference between two bracket pairs, if that makes sense.
Yeah, but what is the resolution width for the extension?
Yeah, it's
And do you
squared,
want to say
Gilbert.
anything about the? I mean, the CNF formula said it. You hinted that it's somewhat delicate, but anything about encoding? Like, will I use
Thank you.
indicator encodings? Will I use bit string encodings, like binary encodings, or
No,
I
you
don't
can do
care,
whatever.
or okay, not so important.
No, you can. In fact, we introduce all extension variables that you could imagine on a single index. So every index will be so every index will correspond to roughly log n many variables, which basically encodes what kind of a bracket do I have here and where is my body. So you need roughly log n many bits. But then we can just introduce all extension variables on these log n bits, which is roughly poly n, right? And then over this formula, over these variables, we can then just do a 3CNF encoding of whatever we want. So really, you can do whatever you want. It's very stable.
But you want log n bits for the neighbor? I mean, you could. What would happen if I just have indicator variables for all the pairs, whether the positions are paired, or this I don't want, or I shouldn't ask about these low-level, uninteresting questions.
What again? Sorry again.
So it seems like once I have a bracket, I have log n bits to tell me the position of the matching bracket.
Yes.
So I'm just trying to understand. So I don't even know if it's relevant, but suppose you could imagine like that I would have n variables, namely just for every position. Is this position the pair?
Yes. Yes.
And would this this is stupid, or it wouldn't really
No.
make any difference, or
No, this would also work.
okay. And the lower bound is somewhat robust to these, as long as you don't do anything obviously dumb, like basically your prosecutor defendant game will be played on brackets, and then you just make sure that this lines up with the CNF formula in some way.
Yes. Yes. You can somehow translate between these different formulas back and forth, and then you don't lose anything significant.
More questions before we take a break? Or should we?
So yeah, so I guess we'll meet again in a few minutes, and then I'll tell you about the proof. Yeah. It will be nice. Like I have slides. It's not going to be hard. It's probably so.
So we are back after the break to hear about some of the proof ideas in the results that Kilian told us about before the break. So without further ado, Kilian, the floor is again yours.
Perfect. So So, okay. So
can I ask a question like about the lifting thing? Like where does the exponential size come from? Like why it's like quasi-polynomial depth and like can you elaborate a bit on that?
well, I mean, you just like the more you decrease the depth, the more size you require, right? So it's just for polynomial depth, you get exponential size. But if you go to quasi-poly, you couldn't really say anything.
No, I mean yeah, I guess I just don't see like immediately how do you like get it from like quasi-polynomial quasi-polynomial round on depth? Where do you get like the exponential round on size?
Because to reduce the depth, you need to increase the width, and the width lifts to the exponent in the size.
Oh, oh, I see. Oh, okay.
Oh, very good. Yes.
Okay, yeah.
Much better than I could have said. Thanks. All right. Anything else? Good. So our goal is to devise a strategy for the defendant such that the prosecution needs n to the omega of log n over log w rounds to win. Okay, I hope everyone is on board with this code. All right, so what do we want to do? Well, we are not very smart about proof ideas. And really the only thing we could come up with was just to hope that this recursive strategy that I showed you earlier for the prosecution is in some sense optimal. And we just want to force the defendant to somehow, we want to force the prosecution to somehow follow this recursive strategy. Okay? This is not going to be exactly the recursive strategy, but really the idea you should have in mind is that we want to force some kind of recursive strategy upon the prosecution, which resembles this recursive approach. Okay? So the main idea is to force the prosecution to follow the recursive strategy. Okay. So let's look at an example. So suppose the prosecution remembers these 4 bracket pairs that I drew here. And so we already know that the interesting stuff is happening in this separation interval, right? So here I have the separation interval. And if the prosecution queries anything outside, it's easy to answer, right? If the prosecution answers something to the left of the separation interval, I can just answer with a red bracket pair, like close together. That's easy to answer. And I'm always safe to do so because everything is red on the left side. And on the right side, everything is blue. So I'm safe to just answer with a blue bracket pair.
There is an annoying odd even issue here that you're skipping over, but you're somehow taking care of this.
Very good. Very good. Yeah, I'm hiding. Yeah, maybe I should mention I'm hiding some technical issues or some technical things. Among others, like one of them is this parity issue. Because currently, as I introduced the formula, we always need to have even distance between 2 brackets, because otherwise we cannot fill the things in between. Like if we have it odd sized, then we cannot really do brackets in there. So what we actually do is we allow a special symbol, which is like in one position, you're allowed to open and close the brackets. So, well, we actually draw it like this. So this is like a special symbol, symbol to open and close in one index. There are other ways how we can handle this, but this seems to be the cleanest, so we don't have to think about any even odd constraints. Very good. Anything else? All right. But I hope we can agree that really the interesting stuff is happening within here. So what we want to do is we want to have a recursive strategy for the defendant that somehow plays on some interval. And we always want this interval to be the separation interval. Okay? So we start out with a defendant that plays on a large interval, and then it will start to give answers, and at some point it will go like recurse onto a smaller interval and invoke itself on that interval. So in this picture, what would happen is that the defendant actually invokes recursively on here. Okay? Because that's what's interesting in there. And after some time, this recursive call will return. Okay, and we should think of this as okay. So this recursive defendant somehow returned and gave up on this interval. So it got too tight in there to answer anything reasonable anymore. Okay. So this means now our job is to somehow find another nice interval which is empty, like that we have not given any answers, and then recursively invoke ourselves again on this large interval. Okay, so what we want to do is we played on this interval, and now, well, we look at our whole interval. We'll find a large interval which is free. In this case, it's clearly this one, right? We have lots of indices without any bracket, right? And then we want to move the separation overall or interval to over here. Okay, so this is move the separation interval. Okay.
Is the way I should think about this is, because you didn't tell us about this recursive thing, but as long as the separation interval is large enough, I will be able to play successfully because prosecutor won't be able to force a contradiction because he has too little memory. Is that how I should think of it?
It's large, so I can answer a query or some queries without having any issues.
Mm-hmm. Yeah, but how do I mean, what does it mean to return from this invoke recursively thingy?
I'll formalize this on the next slide. Okay.
Okay.
Just want to give some intuition of what is happening.
Okay.
So yeah, so we can return from this recursive call, and now we want to move to some other large interval, and we want to do a recursion on there. Okay. And for this, what we need to do is we want to move this separation interval. And currently this interval is large and empty, but it's not a separation interval because the left side is red, but the right side is also red. So we want to make the right side blue. Okay. And how we do this is we wrap all the red brackets to the right of the supposedly new separation interval by blue bracket pairs. And now we actually have moved the separation interval to here. And now we can invoke ourselves again. This is very similar to what the defendant played against the recursive strategy, right? Because there we were in some separation interval, like here, we're in this separation interval, but now we actually knew that the defendant, the prosecution, as the next thing will play on this part here, right? So we could switch over to the other one by just wrapping this one bracket pair here. And then like play on there. Now we don't know what the prosecution will do, and so we need to have a bit more a stable a bit more stable strategy. And what this means is that we don't just jump to the interval that we would expect the prosecution to make queries, but we just move to a large one, which is free. Okay. All right. So let me formalize this a bit better on this slide. So we have a defendant which takes as an argument an interval. So we should think of this as the separation interval and a recursion level. Okay. As long as we have a low recursion level, we will do the following. So for n to the epsilon times, we'll find a largest interval within I that has no answers. Okay. So this may be equal to I itself. Okay. So for example, in this example here, if I is all of this, right? If this is I, then I sub I will also be the whole interval. And now what we do is we move the separation interval to I sub I if necessary. In our case, it's not necessary. And then we recursively invoke ourselves on that interval. We increase the recursion depth. Once we reach the maximum recursion depth, which is L0, which we should think of as some epsilon times log n over log w, then we are ready to actually play one round of the game. Okay. What do? We get some index which is queried from the prosecution. And if I is less than half of our interval, right? Our interval is limited by A and B. If somehow the query that comes is on the left side here, it's maybe here, then we answer red. Look. But if the query would be further to the right, then we answer blue. And just a bracket pair which is right next to each other. We don't want to give away any covered indices. We want to answer as tightly as possible. Okay.
And the invariant you're maintaining at all times is it true that without loss of generality, prosecutor will in fact ask in the current separation interval because you're fully consistent outside?
You cannot do this without loss of generality. I don't know how. Because it might be interesting to cut a very large interval into smaller segments so that the next time we do this recursive hopping, we go to a smaller interval. Does this make sense?
But then I don't understand, how do you deal with, in the first n to the epsilon, how do we deal with questions? Or you just take a question?
We don't do any questions.
Okay.
Here we are just somehow trying to evade, trying to find large intervals. That's all we're doing there. Only in here, once we have recursion level like L0, which is epsilon log n over log w. Once we have a very deep recursion level, then we're ready to play one round of the game. Let me do an example.
Yes, maybe.
So let us think of so let us set n to the epsilon equals 3 and also L0 equals 3. Okay. We first invoke the defendant with the full interval. So we invoke the defendant with all of n and 0, or maybe 1, let's say 1. And now we play the defendant. And here I have the different intervals on the different recursion levels. So initially, we invoke the defendant with the full interval, right? So this is the interval of I1. Then we start this for loop, and we find the largest interval without answers. This is I2. It's again the full interval. Okay? We move to separation interval. There's nothing to do. We recursively invoke ourselves, and we do the same again once more. Okay?
So I1 equals I2 equals I3 here.
Yeah.
Because this was confusing me a bit.
yes, it will get more interesting in a second. So now
Okay.
we are on the recursion level 3. Okay, so now because L0 is equal to 3, we can actually play the game. All right. So what happens? Well, we get some index queried, maybe this guy, and then we answer accordingly. So we answer according to the closest endpoint. So here we answer with a blue bracket pair, and then we're done. Okay. So we return from our recursive call. We can erase I3. And now we'll find, again, the largest interval in I without answers. And now this is clearly the first interval here. Now, again, we get some query. Let's say we get the query.
And now you don't
here.
have to move the separation interval because it was already there.
Yes, exactly.
But suppose it would have been your blue brackets for some weird reason would have been red, which I guess they wouldn't have, but
in this case, it
they
cannot be, but in future calls, it might very well be the case.
And then you would now enclose
And
them
then
in blue.
we would have wrapped it, and we can kind of forget about it. And then we would have the
I'm not sure I
separation
understand
interval
what you
here.
mean by forget, because I'm not in charge of the forgetting, but definitely
Well,
what we can do at that point is a sort of, as a defendant, we're committing to the prosecutor has not even asked about this, but you can actually
Yes.
say up front that if you do, then here's what my answers are going to be.
Precisely. We can give it away for free, basically. We just reveal it to the prosecution.
And what I meant before is now that the point is that why I would expect, so maybe I didn't ask the question well before, but given this, is it true to say that without loss of generality, prosecutor will now play on the left? Because any question that prosecutor will play on the right now, that you could just, you can just fill in blue brackets all over the place.
It's not obvious. You cannot do this without loss of generality.
Okay.
And the problem is that suppose we're playing on this interval here. Suppose I3 is now this interval. So now the prosecution actually knows that the next time we go up in the recursion, we will actually try to find a large interval here or here, right? We'll jump either to that one or that one. And maybe one of these is very large, so it's beneficial for the prosecution to first cut it in half, so that the next time we go one level up, the window is smaller that we have to choose. Does this make sense?
Yes.
Right, it might make sense. Suppose this is very large. This here is very large. Then it might make sense to actually query something in the middle, so that the next time we have to choose this I3 interval, we are actually forced to choose a much smaller interval than otherwise. And this might be useful for the prosecution. Who knows?
You could then ask if you could get a better lower bound by somehow declaring. You could want to say that your interval should still be what it was before because this was not a dangerous query, but that is not true, maybe.
And
like such a big, beautiful interval should not be spoiled by this query. But maybe that's not true again.
Yeah, this is a difficult question to answer. I cannot say what what will help to improve the lower bound, but I suspect not. Let me put it that way. But I'm not sure. Yeah.
But it's a good answer. Thank you. This was helpful. Okay, so given, because again, the prosecutor knows how the defendant is going to play, and for this reason, even if the big, beautiful interval doesn't seem dangerous now, making it a bit smaller will influence how defendant plays in the future, and so that could make excellent sense.
Yes, sense. Okay. So yeah, okay. So let me just play a bit more this recursive thing to get a feeling for what's happening, right? So now we do this again. We get the this was blue here, right? So we get another query here, red. Now we're done with I3 and also I2. Now we move I2 to a large interval. Well, it just happens to be this separation interval. And then we continue playing on here. So now I3 will be also the whole interval in here. Then we'll get a query, maybe this one, and so on. The interesting case is actually when the separation interval needs to move, because then we need to wrap these brackets that are ill-colored or like wrongly colored in between. Okay, I don't know how well I explained this. Are there any questions?
How long are we actually play? So somehow you go down a certain number of levels. Oh, you always just you only answer once you're down to level L0.
Precisely. So we can
And
think
then you
of this.
answer a question, then you go up
Yes.
and move the separation interval. But what will force like more recursion levels going up? Or no?
Well,
There are no, like you just do the splitting.
So we do this on every level n to the epsilon times.
Yes.
And once we have done it n to the epsilon times, we give up. Okay. You could think of doing this more often, but then somehow the fear why you want to stop is that you can get larger and larger bracket pairs. They cover more and more indices.
I guess one thing I didn't understand, the for loop runs to n epsilon, but then the answering questions and moving the separation interval, will that sort of only happen at level L0 all the time?
The moving the interval always happens at above levels, right? Like here we have L is less than L0.
I don't see where do you go back
Here
to
we move.
L0 minus 2? I don't see when this happens.
Well, once we have played a round of the defendant, we return to L0 minus 1.
Yes.
If this happens to be I is already equal to n to the epsilon, then we return one level above. You can really think of doing a DFS over a tree of depth L0 without degree n to the epsilon. Right, we walk down here, then we do blah, 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 blah. Once we're down here, we go up, we go to the next one, we do here, and so on.
Sorry, I think I was confusing I and L. How are these two parameters related?
So L is the recursion depth,
yes,
and I is the out degree of every recursive call. How many recursive calls you make on a certain level. Right, we have for each recursive call on a certain level, we do
okay, now
I
I said, sorry,
iterations.
yes, I didn't get this. Okay, good.
Right. And then we invoke the defendant, and then we of one larger recursion. So you should really think of as having a tree and somehow exploring this tree in a depth-first search fashion.
How do I deal with prosecutor forgetfulness? Is that clear from here, or?
Oh, very good. Well, if forget, just return. We just do nothing. That's fine. It's one round. We just want that in this tree, right? We have this huge tree with n to the epsilon log n over log w many leaves. We want to argue that in every leaf, we have played one round of the game. And we want to survive this whole exploration of this large tree. Or in the recursive language, you want to survive while this recursion is ongoing. Further questions? Okay. So I don't think it's obvious how you can even get stuck at this point. Like, how could it be that in this strategy we actually die or like prosecution catches us lying? When can this happen? It can happen in two places, right?
Kilian, I think, sorry, one final question. I guess what I was confused at the capital II, it's actually the I, is it true that the IIs actually have two indices? Like they're also indexed by the level. Is that true?
Yeah.
I think this was what
This is
confused
the
me.
level. This is the level here. I was afraid. And this is I, which is the for loop. These are different indices.
Yeah, but sort of, so what would happen at the very outset is like I1 for level 1 is everything, and then for level 2, I1 is still everything, and then for level 3, I1 is I level 1, I level 3, 1 is still everything, and now we play. And then we
Yes.
go back, and now okay, so actually like capital I sub Li are the intervals we're playing over. Okay, sorry, I didn't
Yes.
see this. I got myself confused. Thanks.
Yes. Yeah. All right. So yeah, so how can we even get caught by prosecution? So this can happen in two places. One is if here at some point we want to answer a query, but our interval is so small that when we answer this query, right, our interval is like just of size 2, say, and then we have to answer a query in here. Well, this is very annoying because no matter how we answer, prosecution will win. Okay, so this is one way how we can get caught. And the other way how we can get caught is that here, when we move the separation interval, then we need to wrap these other bracket pairs potentially. So let me draw this, what I mean. So, right. So maybe we just played recursively on here. So I sub I was here, right? And now we want to move this recursion interval to this large area over here. And for this to be able to do this, we need to have enough space to actually wrap all these bracket pairs in here without causing any contradiction or like without introducing a solution. So what this means is that we need enough space over here, right? This needs to be large, say of size larger than 5. And wherever we're going to needs to also be large enough so that this blue bracket pair doesn't touch this red bracket pair. Okay. So, like in summary, what I'm claiming is that if we can establish the following, like that the following holds. Like the previous discussion, I want to summarize as follows. Namely, like if the defendant is always instantiated with a large interval, like of size 1, like you can think of as the size of I is larger than n to the 1 minus epsilon. Okay, it's huge. Okay, like even on the lowest level, it's this large, right? If we always instantiated our defendant with a large interval, then the prosecution can never catch us while we're playing this strategy. Okay? And really the proof of this lemma is what I tried to explain here, that there are two cases where you can get caught, either when answering a question in the lowest level, But we're assuming that now this is huge, right? This interval on the lowest level, so we cannot get caught there. And also when moving, because where we just returned from, the interval was so large, this means that we have always space to answer blue here. And also we can always answer blue here because the interval we're going to is very large by assumption. Okay? So all that remains is to establish this lemma. So we want to establish that while we're playing this recursive strategy, all the defendants that we invoke, they're invoked with a very large interval. All right. And now, well, how would you go about proving this? Right, we have an interval I, and in this for loop, as we go around, we always want to argue that we can find a large interval. So we somehow want to have a statement that every time we return from the recursion, not too many indices are covered within the interval I. Because if this is true, then I can always find one large interval. I mean, we know that prosecution can only remember few bracket pairs. So the only thing we need to worry about is that these few bracket pairs cover a lot of indices within the I interval. Certainly, if this is not the case, then I can always find the largest interval I without answers, which is roughly of size n over w. Or, sorry, size of I over w, approximately. And then we need some constant here to accommodate for the things that are covered.
Just to clarify, when you say cover, then you also mean whatever is inside the bracket pair?
Yes. If this wasn't clear, so what I mean by covering is if you have a bracket pair, then I'm saying all these indices are covered. Or I mean, this index, this index, this index, like all indices in between the left and right bracket pair are covered. Okay. Any other questions? So let me repeat. You know, the prosecution can only remember few bracket pairs. So the best we can hope for is, well, the prosecution may just remember W bracket pairs within the interval I.
But
So
inside covered intervals, you
largest...
are consistent. Is that right? The inside, if an interval is covered, then the defendant has also filled it in a consistent way and could refill in that consistent way. Is that correct?
Yes.
Okay, so therefore it's not dangerous for us if prosecutor places in a covered interval. That would be like a stupid thing to do.
Precisely. Covered indices were somehow built up in a way that we can always fill them up. Like right, we just wrapped the things and everything is fine. Okay. Yeah, but what we want to establish is that every interval I sub I is actually large. So we know the prosecution may remember W bracket pairs within the interval capital I. So at best, we could hope for a large interval, which is of size I over W, which is empty. Now we want to argue that, well, few indices within I are covered at any given time. And therefore, well, we can prove something like size of I over 4W, lower bound on I sub I. And this will result in this kind of bound. Okay. So just to write down what I just claimed. So if the defendant is invoked with a large interval, then after the defendant, like after something returns, right? Then I want that at most order of n to the 2 epsilon indices are covered in I. Right. So once we return from the recursive call, within capital I, at most n to the epsilon indices are covered, which is really, really small. So then we can argue that this defendant here is always instantiated with a large interval. Okay. And hope this is clear. The cover lemma implies the required. Questions? All right. So it remains to prove this cover lemma. So we need to argue that after we did some recursive invocation and this returns that few indices are covered within the I interval. And we can do a naive attempt at just trying to prove this like by induction. Okay, and so the naive attempt is by induction on L from the leaves to the root and to 0. So we start at the largest recursion depth and then do the induction backwards. And on I from 1 up to n to the epsilon. So how should we think of this, right? We have a defendant that was instantiated with an interval I and some level L. And this guy spawns new children, so to say, of defendants on the interval I sub I and of recursion level L plus 1. And we have a few of these. Okay. So now, if we just naively apply this inductive hypothesis, right? So because we are doing this induction backwards on L, we may assume the induction for the children below us. So we may assume that these guys have cover at most n to the epsilon times w to the L0 minus L many positions. Okay. So all of these cover n to the epsilon times w to the L0 minus L many positions. So if we just naively apply this, then we would get that we cover in capital I n to the 2 epsilon times w to the L0 minus L0 minus L plus 1 positions. Right, we have n to the epsilon children. Each of these cover few indices. And if we just do a naive attempt, we'll get something like n to the 2 epsilon cover now times w to the L0 minus L plus 1. If you would continue this recursion in this way, you would in the end cover somehow n to the L0 many positions, right? Which is clearly terrible. Like we want to argue that we always cover few indices. So actually what we want to do is we don't want to pick up this 2 here, but we want to pick up a W factor there.
But is it that you will take advantage of forgetting of the prosecutor?
No, so what this argument so far has not used is that the prosecutor is memory limited.
Yes.
So what we want to use, is that memory limit. Okay. Because currently we just assume that for every recursive call, the prosecutor may remember everything, right? But this is unreasonable because, I mean, the prosecutor probably remembers W many bracket pairs from each recursive call, right? So now we want to have somehow an argument that can argue that, oh, by the way, it's more like a factor of W instead of n to the epsilon because the prosecutor is limited in memory. All right. So here I just have the same that I try to write now. So, but if we want to use the fact that prosecution is memory limited, we somehow need to argue that not all bracket pairs can be merged into a single bracket pair. So what I mean, what would be very bad for us as defendants is if the prosecutor can take some two bracket pairs, like these two red guys, right? And currently the prosecutor needs to pay two memory cells to cover all these indices, right? So what would be terrible is if it could happen that somehow the prosecutor can replace these two memory cell by these two bracket pairs by a single bracket pair. Because then it only has to pay one memory, but covering the same amount of indices.
Is this what your move definition takes care of?
No. The move definition is not doing anything.
Doesn't it wrap up these two by two blue intervals instead of one? Or
Yes. So okay, yeah, but I need to argue that if you remember these two large red intervals from the first two recursions, say, then by the end of the n to the epsilonth recursion, you cannot do this wrapping.
okay.
And clearly, like in a single step, as you pointed out, this cannot happen because move only like minimally wraps the red bracket pairs. But if you do this often enough, right, it could happen that these suddenly get merged together eventually, or over these n to the epsilon many recursions.
So we have
Does
to
it make
make
sense?
sure that they're sufficiently far apart somehow.
Precisely. Very good. So what we want to do is, so we want to argue that bracket pairs from different recursive calls are far apart. Okay. And we can do this because in each move operation, we only cover, like, increase them by a little bit, and we only increase n to the epsilon times. If this distance is much larger than, say, w times n to the epsilon, then these bracket pairs can never, like, suddenly merge into one. And so this statement, we formalize this statement as follows. So what we want is that when we return from a recursive call, then the square root n, or n to the 1/10 many positions to the left and right of the interval may only contain trivial red bracket pairs or trivial blue bracket pairs, depending on whether it's on the left side or on the right side. So if I have to draw a picture, right, we're within the interval I, and we have some interval I sub I here. Now what I'm saying is that the leftmost and the rightmost indices is like a 0.1, and n to the 0.1. So in here, I can only have red bracket pairs. So here, red and trivial, where by trivial, I just mean they're right next to each other. So a trivial bracket pair is just a bracket pair that only covers two positions or two indices. And on the right side, I only have blue trivial bracket pairs. And now, with this buffer lemma, we can argue that any two non-trivial bracket pairs from distinct recursive calls are super far apart. So that no matter what we do in our move operation, when we move from one interval to another separation interval, and we wrap these brackets in between, we will never merge these bracket pairs. Because we never merge them, this means that in the end, you cannot pick up this n to the epsilon factor here, but we'll only pick up this w factor. Because, yeah. Okay. This is the entire proof. Does anyone have questions? I'm a bit afraid I lost you a while ago, but yeah. So, right, so in the end, the argument is really that if you have a non-trivial bracket pair originating from this recursive call, and a non-trivial bracket pair from this recursive call, then in between here, we have super much space, so much space, so that no matter how often you do this move operation, which you do n to the epsilon times, these bracket pairs can never merge together. They can never grow together. And because they can never grow together, this means that you can at most remember W many bracket pairs from distinct recursive calls, which will have like size of whatever you can prove in each recursive call. Plus a little bit more because move can also cover like n to the epsilon times W many other positions, but we can ignore this. It's just a little bit more. All right, so this is it from my side. So conclusion, we just, because I didn't talk much about monotone circuits, right? We showed that there is a monotone function with a monotone circuit of quasi-polynomial size, but any such circuit which is of polynomial depth needs to be huge, namely almost exponential size. And some open problems, the first one is, can we actually use our formulas, like these bracket formulas, to give applications to Weisfeld and Lehmann? We kind of know that they're related to graph isomorphism, but we don't have the explicit reduction, which we would need to argue that the supercritical trade-off actually carries through. And remember that the concurrent work actually has applications to Weisfeld. So I would also like to have that, but yeah, we don't.
I mean, you would get, if you could get a nice correspondence, your robustness for Weisfeld-Lehmann would be much, much, much better, right?
Yes, but only for logarithmic number of rounds, not for constant number. Which, as I understand, logic people don't care about logarithmic number of rounds.
That's a good point.
So has been claimed. I don't know. Don't know enough about it.
That's actually a good one. Okay, so that's one reason why you would actually care about constant width also.
Precisely.
That's a good point. But
yeah,
still, I mean,
sorry.
I think it would still be, I mean, the robustness as such would be interesting.
Yeah, I agree. No, I would like to prove this, but I don't know. And then finally, right, if you remember, like our size upper bound is quasi-polynomial, but our depth restriction is really polynomial in n. So now the question is, what happens if we only restricted like polynomial in S, like in this n to the log n, can we still get like a size blow up, or is there just nothing happening there? I don't know. And finally, like a question that I like.
That is another
is-
robustness question. Like you'd like to be able to argue lower, like trade-offs for larger depth than, is that right?
Yeah, for larger depth, but equally strong.
Mhm.
So I want to increase the depth, but retain the size exponentially, or weakly exponentially.
And do you know that it's, sorry, but is this like false for these formulas, or is it just that we cannot establish it?
We don't
Okay,
know.
so
This is, I believe this is connected to proving tight lower bounds. If you can prove tight lower bounds, you would get this thing here. I hope I'm not saying something wrong, but I believe this is the case. And finally, a question that I really like is, can we prove conditional supercritical trade-offs for circuits? Not monotone circuits, but just normal circuits. This is not my problem, by the way. This is a problem by Pitassi, Robert, Flynn. Or that's at least the first time I've heard of it. But I really like this question. Yeah.
is it clear what the conditions would be? What kind of conditional would you hope for?
Take anything. I like crypto, some pseudorandom generator assumption, I guess you would want. But I don't know how to do this. Yeah. That's all from me. Thanks for listening. Hope you learned something.
Thank you, Kilian. So I'm like applauding on behalf of our whole audience in cyberspace. I think that there are still possibilities to. We also have some clap emojis in the participant list. Questions, comments. Final chance to bug Kilian for today before we release him after working hard to entertain us.
I think there are no questions.
No, it's all crystal clear.
Yeah.
Is it clear how this, I mean, how these formulas, so we're very resolution focused here. Is it clear what would happen for these formulas for other proof systems? Or maybe we don't, or we're just using resolution because it gives us applications elsewhere? Or would it make sense to think about like, okay, what if you throw, I don't know, polynomial calculus or cutting planes at this?
Yeah, so I can tell you a bit about this. So right, if you look, so how we ended up with this question or with this formula was actually that we studied something else, which is related to TFNP. And there we have PLS, which is basically resolution. And we have the PPAD, which is Nullstellensatz over GF2. A unary Nullstellensatz, I guess. Unary Nullstellensatz.
Where you're taking as a given that there are total NP search problems and there is a standard but non-obvious relation in which somehow different total NP search problems can be paired up with proof systems in some kind of way that they're kind of sort of the same.
Yes. And what I want to tell you is that like this bracket problem lives somewhere within this TFNP landscape. And it actually lives, so it lives somewhere between UEOPL and EOPL. So, I mean, this is, okay, so maybe I should mention this is work with Gilbert, Maystre, I guess, It's his last name, Maystre and Hollander. So I should Hollander first. So this is work with Hollander and Maystre. And you can actually place this problem between EOPL and UEOPL. So here is the bracket problem somewhere. We don't know whether it's EOPL complete, but we know that it's at least UEOPL. So this is telling us, I wanted to say that you cannot do something, but this doesn't make sense. Yeah, maybe I started saying something and it's unrelated to your question.
That's fine.
Yeah, it's unrelated. I do not know what happens in polynomial calculus. Because,
but an open problem that you're not mentioning then is pinning down in the TF&P universe where the brackets are.
Yes, this is open. So, but it's very funny. So depending on the definition of bracket, it jumps around in here. So in particular, there is one version which is PLS complete. There is a version which is UEOPL complete, and one version which is between EOPL and UEOPL. We discussed the version that lives between EOPL and UEOPL. We don't know where. Yeah. So, yeah. Yeah, I don't know. I was also wondering at some point, so whether this PLS complete version of bracket, whether you could prove something along the lines of any supercritical tradeoff for resolution is because of the bracket problem. So like to argue that there is a complete problem for supercritical tradeoffs, which is hopefully this bracket problem. I mean, honestly, I just thought it's too optimistic to even think about it. But maybe it's worth to think of whether there is a complete problem for these supercritical tradeoffs. I think that would be really cool. So like you would have some statement which would say that if you have any formula which is a supercritical tradeoff, then it is because of, like, it can be reduced to this one problem, and this we just need this one problem. I think it's a bit optimistic, but I don't know. Maybe one can prove such a statement. I would really like it.
Will this help us find even more? I mean, the interesting thing is arguably with this formula, if you compare to the work that you mentioned and reviewed in detail by the Resenda and Janet et al., this is, again, taking Zetin and then applying some operations on it. Again, taking the tools from our toolbox and hammering on the formula. Then the end result is beyond recognition and we really don't understand it, but we can prove some results about it. In some sense that I don't know if I can define mathematically, this formula is kind of an original formula. I mean, it's not a formula plus a tool applied to it or a gadget with which it has been lifted or something. It's like, it's a combinatorial principle, right? And it's a combinatorial principle exhibiting supercriticality. And I guess I don't think we know of any other principle exhibiting supercriticality in that sense, unless you maybe, okay, you can debate whether Zetin formulas on very narrow, very long grids, is that somehow a combinatorial principle or not? This can be debated. This, I guess, exhibits a supercritical trade-off also. But it's interesting. This is a new combinatorial principle, and it has sort of natively interesting properties. Can we, can we get more combinatorial principles with these kind of properties? Or you were lucky, you were out in the wilderness and you happened to stumble over this and brought it home as a specimen to be investigated in the lab?
Great question. I have no idea how to create new ones. Yeah.
LLMs? Okay. Any before the whole discussion gets completely out of hand, do we have any final questions? Or otherwise,
Not sure if
yes.
this is annoying, but do you know anything about space?
Yeah, I don't. It's
What was
a
the
good
question?
question.
Sorry.
I'm asking, is there anything that can be said immediately about the space, about these formulas?
Excellent question.
Yeah, great question. I conjecture they exhibit a supercritical trade-off for space also. That's my
Is it even
conjecture.
clear what the upper bound, I mean, the with efficient refutation that you would get? Can you is it clear what the space is?
I don't remember. Do we? You remember? We discussed this at some point.
Because if it's very deep, then sort of the viewing it as a tree-like proof, that tree-like proof will have large space.
I mean,
But
depth and space are not.
no, absolutely. But then that says that you can't just, I mean, normally like when you're doing proofs, how you get them to be space efficient is basically you get a shallow decision tree and then you argue that, yeah, size might be terrible, but since the decision tree is shallow, the obvious strategy, even for tree-like resolution, will give me a space efficient proof. What I'm saying that this will clearly not fly here because the decision tree for low width is very deep, and so the naive simulation of that will then have very large claw space. So you'd have to do something clever, something DAG-like when you're staring at this deep proof. Is it obvious that you can do something clever?
No.
Or?
I'm not sure if this view of viewing it as a depth first search over a large arity tree can give you a better recursive bound such that you get, I don't know, upper bound n.
Oh. Okay, wait. The fan out is n to the epsilon.
I'm not sure about the
What's
depth.
the depth of that tree?
N to the 1 minus epsilon.
It was this recursive depth L0, right?
Yes.
What is L0?
Log n over log w.
Okay, so if we can somehow view, would that be space efficient then? Maybe. I'm not immediately sure whether this like maps to a resolution proof, but if I have a, like, I mean, if I just looking at, if I have a tree with log n layers and fan out n to the epsilon and I'm doing a black pebbling on that tree, then I guess what is the pebbling price then? Then,
But should it be something like n to the epsilon times the depth of the tree?
yes, or even better, but n to the epsilon times the depth should be like an upper bound, no? So then it might be space efficient. But I don't know if that view corresponds to what the resolution proof does.
Yeah, I'm just asking. I mean, no obligation of thinking on that.
I think it's a very good question.
Yeah, so I mean, you should talk to Turi. Like I talked with him about these questions, but I don't remember. I did other things in the meantime, so I forget. I'm sure he made notes and he has everything written down, right?
Yeah, okay. I will fly to Copenhagen tomorrow morning. Be prepared.
Do that.
Okay, thank you so much, Kilian, again for this seminar. And yeah, I think we'll wrap up now. So again, thanks so much for presenting this for us. It's really nice.